Right, well, thank you everybody for coming tonight, and I hope you'll find this enjoyable. And I'm going to speak more on the data, information about climate, not so much on climate science as a total topic, but what is actually happening. And so my title, if you like, is what is really causing weather and climate change. Now, weather is changing all the time. It changes overnight. That's called the diurnal cycle. It changes weekly, monthly, seasonally, annually, and as Nick has already pointed out, it changes over a long period of time due to molecular cycles, the elliptical orbit of the Earth around the Sun. And there are other factors involved. I should just clip in here that I've never met Nick from before tonight. He hasn't seen my slides, I haven't seen his, and so if there's any clashes, the only clashes will be with interpretation, insights and understanding of these factors. And I just want to say thank you to the pastor here for welcoming us, having us here at your church, and the elders and the board. I appreciate that. And by the way, it's the first time I've ever followed a main speaker. Nick Main. Okay, so what I'd like to do is ask the big question. The big question is, how much is anthropogenic, or how much is man-made? Now, in case you're offended by the title man, man means mankind. All through the Bible it's mankind, that's what it's meant. So how much is mankind made? And I'm going to give an overview so you'll see where I'm going. And it's like the Irish preacher, I'm going to tell you what I'm going to tell you, then I'm going to tell you, then I'm going to tell you what I told you. That's a three-point system that you already put, Peter. I'm going to review something we've all put us all on the same page, what we had at school. And then I'm going to uncover what is really happening and in a sequential manner, unlock some of the key weather issues that are not publicised on the press, not publicised often in the media as well. I'm going to look at composition and concentration of the atmosphere because that's very important. And then look at solar radiation versus re-radiation back from Earth, because that's also important. That's the dominant factor in terms of changes. So we'll see that shortly. And then I'll look at the various mechanisms that actually cause these things that are not often expounded. And I'll finish up to show that there's no climate emergency whatsoever and why, as you'll follow it through. So I want to start off with a little issue because obviously some people are a bit concerned. So I'm going to answer this little issue that has been raised before. How many in this audience, we all know that things are held together by attraction, aren't they? Does anybody in this room know of anything held together by repulsion? Anybody? Put up your hand if you know. That sounds good.
Surface tension?
What's that again?
Surface tension?
Is that repulsion? It's actually a drawing down and a contraction of forces on the surface molecules because they have forces in and there's no forces above because there's air there, so it's an internal attraction. This is actually held together by repulsion. Now, I just wanted to raise it. I'm glad you did, so I don't be worried that I didn't drop that. I want to show you something now because the whole audience said, no, I don't know anything held together by repulsion. So what I'm going to do is show you something that's held together by repulsion. Now, the reason why I'm saying this is because there was a total consensus here that nobody, apart from our friend here, who raised the point, which I'm glad you did. This is held together by repulsion. Four elastic sticks pushing against each other forms a repulsive forces at each of these key nodes to hold the thing together. So what I'm trying to say is consensus will get you nowhere. It's not consensus of what the population believes, or what the government believes, or what NIWA believes. It's what actually is happening. And just to prove there's no glue involved with that, and I can set it up for you later. So I just want to highlight a point. We've got to have information, facts, and we've got to have data. And we'll talk more about that. So my intention, my sincere aim, is not to tell you what it is, but to outline the factors surrounding weather change in particular. And so I'm going to provide evidence. That's my main function tonight, is evidence. And I'm on the handout sheet, you'll be given a handout sheet if you want it. It's got two references. That's all you need, and you can go on your home computer and do your own investigation to prove what I'm saying or validate what I'm saying is either right or wrong. The I factor is the number with the I factor, but information, insights and interpretation is what I'm after. Okay, so let's start back with heat transfer mechanisms that we all had at school. Well, the first one we had was conduction. You remember that? And conduction, if we hold a particular rod and we put heat on one end or heat one end and hold the other end, after a little while we've got to let go because the heat travels from a high temperature to a low temperature. The molecules, if it's a plastic, or the atoms, if it's a metal, vibrate and they get more and more active and they transfer energy, and that's called conduction. We had that at kindergarten, we probably started that. And then we went to convection. And convection, of course, you had very much experience, and we've had that at school, where if you have a fan, you'll feel the molecules hitting you and taking the heat away. So there's a fan. If it's got a heater in the fan, it'll feel the warm air. So some of you in your lounge rooms have got a warm air blower. So that's convection. Of course, we've all been outside, so breezes and winds are a good example of massive movements of air movement. The third one we had at school was radiation. Now radiation, we all are well aware of it. If we go outside on a sunny day, we feel the heat. The heat is on. And that's 93 billion miles away. The sun punches out radiation, hits us, and the only thing that separates us really is darkness or when a cloud comes over. But if you put your hand near a hot plate, you can feel the radiant energy coming. If you put your hand on it, you go back to conduction, and of course you get a bit of a sizzling on your hand as well, and you wouldn't want to do that. So all these three are driven by temperature differences. They're the ones we did at school. Are we okay? Now, just while we're on the point of differences, if there's a concentration difference, and there's a less concentration here, difference drives it to make it equilibrium, to move towards equilibrium. If it's a high temperature and a low temperature, thermal driving force. If it's an electrical system, high voltage to a low voltage drives the electrons. If it's a pressure in a pipeline, you take a high pressure pump to pump the water to a low pressure. So this is a fundamental of all the basic things. If there's a density difference, for example, if there's a density difference, it goes from a high density to a low density. So it's important to see that driving forces, and that's what engineers are very interested in, are predominant in this world today. Everything works to get towards equilibrium, and that's how it's made, but we never get there. So we say, okay, I've got that, right, that's background. Well, I'm going to say, no, we've only just started. There is more. And I'm going to highlight some of these things. Heat transfer, what else is missing? Well, first of all, evaporation. Evaporation, as Nick has pointed out, 71% of the world, 2/3 of the world plus, oceans, rivers and lakes. So what's going to happen when the sun's energy is going to be evaporation? What's number one in the world? Evaporation, in terms of response from the sun. Number two is not widely known and not widely explained, but we know on a hot day, if we take a coat, I didn't take my coat off, but I thought my chest may sink a bit further. No, I was just thinking that we get a bit warm and we get a bit sticky and uncomfortable. Sweat forms on us, and we know that the humidity's changed. Humidity is the mass of water vapour per unit mass of air. And it's a vital thing because it rises from the sea and the oceans, gets into the air, and of course the humidity down that corner, and that corner is different. There's different here, there's different outside, there's different outside. The humidity's changing all the time. That's why it's almost impossible to model. That's why no one models climate, or they're doing it now, but they can't model it accurately because the humidity driving forces a micro movement. All the computers in the world couldn't do it. Okay, so it's mostly poorly understood, but it's huge. The atmospheric water, up to about 10 kilometres where the planes fly, that's the troposphere that we live in. It's a bit higher near the poles and so on, and the equator is different. But for 10 to 17 kilometres is the troposphere. Above that is the stratosphere, up to 100 kilometres, and we'll talk about that in a minute. So in the first pile, atmospheric water vapour is changing, and it's changing quickly, and it changes all the time. What else is missing? Condensation. So once the water goes up, the molecules move further apart, gas gets cooler, so it's cooler higher up. That's why when you're flying and we have a pilot here tonight, he'll say, ladies and gentlemen, we're flying at an altitude of 10 kilometres and the outside temperature is minus 55. And you say, how does it get frigid? We're closer to the sun, it is colder. Well, it's because molecules are further apart, they don't collide as much, And there's a whole science or engineering in that as well. So what happens is water evaporates, but the clouds now, the condensation of mists, fogs and clouds, this is number 2 after the first 3, number 3, sorry, excuse me. 2/3 of the world, no, it's fine, it's just my little irritation, thank you, thanks, Peter. 2/3 of the world is cloud cover. So now this is massive, massive cloud cover. 2/3 of the world at any one time, land and sea, is cloud cover. What else is missing? Well, let's go to the next one, precipitation. Now precipitation is when the clouds form, water molecules can adhere to a dust particle or they can form a dimer. A water molecule is bent and slightly charged, oxygen slightly negative, hydrogen slightly positive, and you form a dimer. Di means two merge together, form a dimer, polymer, and sometimes, of course, they go to ice. But they're too small particles to precipitate and fall out of the sky, so they stay in the sky as clouds. So then we get, as they build up, or the temperature changes, clouds then give us rain, snow, sleet or hail. Now they have massive effects on weather. That's why you've got to incorporate all these things. And what we're saying here is we've got the combined 2/3 seas, 2/3 clouds, a massive impact on what's happening. So what we had at school was true, but it wasn't all the truth. It's important to see that. We can often have the truth, but not all the truth. And so tonight I want to open up what is truth. Now, you might say, well, surely, what is the big factor here? Oh, water. Well, I'm going to take you one step out of that into this bigger factor, phase change. Phase change. A change of phase. Liquid seas go to vapor water, which is gas, condenses to form water again, comes down either as ice, snow, sleet, and hits it down and forms water again. And so you've got this cyclical change all the time, megatons of it. There's millions of tonnes over the whole of New Zealand at the moment, if you want to sit down and calculate it. Now, water vapour is the only condensable gas in the atmosphere. Because it's the only condensable gas, it behaves differently from everything else. And we must consider it. So water evaporates, humidifies, condenses, precipitates as clouds, ice, rain, snow and hail. Okay? So we're on the page of seeing the bigger picture here. And I've written an article, by the way, a short 3-page if you're interested in the bigger picture. You have an email, you can email me, I'll send to you. Now, let's look at carbon dioxide by stark contrast. First of all, carbon dioxide doesn't evaporate, it doesn't humidify, it doesn't condense, and it doesn't precipitate. But there's still more. Now, I ask you, what do you think there's more? This is not very clear here. What do you think is more? Well, we covered a little bit of it at school, and it was called convection, which is mixing. And this is highly significant, this is. We know that we have breezes, winds and thermals. If you have a mountain and the warm air rises up the slope of a hills or mountain, it forms a thermal. Who goes up in thermal? Birds. They just don't even bother flapping their wings, they just ride the thermal. So do young guys on their hang gliders and so on, they go up there. So glider pilots. And I don't know if the pilot, he won't use thermal for all I know, he's got big jets to keep him going. Right, well now, but think about it. We've got storms and cyclones and hurricanes and typhoons and tornadoes. Now, some of those are just different names in different hemispheres, but we've got jet streams. We've got trade winds. We've got roaring 40s. Look what happened in America recently. It was 40 to 50 Fahrenheit below zero. That's 40 degrees below zero all through the Midwest. Massive piles of snow. What happened? Well, it was, and by the way, 97% of California had no drought. More water there for a long time. Because these were changes caused by the macro movement, the bulk movement of all these things. Now we've also got the oceans. Now the oceans have conveyor belts. Now a conveyor belt is like, I'll take one, a lot of them, but take Miami. Just above Miami, there's warm water and it travels up between England and France. The weather changes there. It is moderated by that warm conveyor belt. Goes up to the Baltic and between Stockholm and Finland and Helsinki, Finland. And in some cases, and it was years ago, you could drive across on the ice. And you can still do it, but you've got to go further north. But you can drive from Helsinki to Sweden or vice versa in a truck. Of course, the warm water does die out with that time and then sinks, and you get this conveyor belt massive conveyor belt. That's a separate study. Now we have tides as well. As you know, we've been down the beach and seen the tides. It's 100, 200 metres sometimes at Browns Bay. Then we have upwellings. So what happens? Warm, moist water coming up will form and come up the top. There has cold water upwellings too, depending on what's happening downstairs underneath. And of course, these upwellings have a big effect because I'll show you in a minute with a little diagram. You can see that you've got jet streams, trade winds, and the El Nino. Now, the El Nino effect is really an upwelling of water followed by the rotation of the Earth and the movement of rotating air around the equator. So these are vital in the total energy picture. You see the picture is complex, as Nick said. It's very complex, but there are certain things we can isolate and contribute from, and that's what I'm trying to do shortly. This is introduction, by the way. I'm sorry about that. Now, look, there are, I'll go back one. Waves are the interactive between, if you have a surface area and you form a wave, you increase the surface area. So the surface area interaction between the atmosphere and the surface of the water is immense. So that's also important. Now, there are others, I'm going to have time to go into them. I want to highlight the sunspots, the Earth's magnetic field. If we didn't have it, we'd die. You've got the southern aurora, and you've got aurora borealis. You've seen the massive clashes of the magnetic field at high altitude, forming these tremendous colours from the radiation from the galactic outer space. We've got galactic outer space radiation. We've got radiation from the sun, and so on. And we've got sunspots. Now, at the moment, last year, and I think it was last month, or maybe the month before, there were no sunspots at all. Some months had 1 or 2 sunspots. There's often 500, 400, 1,000. But I think I looked at this month, no, it was last month, 5 sunspots or something like that. Now, a sunspot is a dark spot. So it's not the radiation so much, the watts per square metre that's hitting the Earth that's changing so much. It's the type or the quality or the wavelength of that energy that's coming. Now, of course, it does fluctuate a bit, but not much. It's very small from the sun. We haven't got time to go into it, but there's the tectonic plates bubbling up. Do you know, 80% of all active volcanoes are under the sea. There's been big films taken just outside the Kermadec Range shelf, just off New Zealand, and it was bubbling carbon dioxide, bubbling methane, and some of it's liquid. It was down deep, it's compressed, 700 atmospheres, and it's liquid, bubbling out all the time. And as Nick mentioned, we've got the Milankovitch cycle, which is the eccentricity of the orbit, so we'll get systems changing with time. And of course the Earth is on a tilt. We've got one moon, not 2. Why do we have one moon? Because the Earth would wobble. And we have one moon, and what does it do? It stops the North Pole moving down to, say, New York or whatever, Vladivostok or something. It's actually stabilising the system. Well, and it affects the seasons, of course. So the facts. Now, we can go on with some of the facts. Let's compare water vapour and carbon dioxide. And we're interested in its effectiveness. We're interested in its effectiveness in concentration and also in radiation. Okay, we're on the same page. We're now going to focus in on these two, water vapour and carbon dioxide. We'll do concentration first in the atmosphere. Now, at school, you were told and taught, and we were all taught, that nitrogen's 79%, right? 21%, and still there. And traces bargain with CO2. And if you go to the web on the page, you'll find that's true too. Well, you find it there, but it's totally wrong because it's all on a dry basis, and it's wrong because it's never ever dry in normal everyday world time. So in reality, there's always moisture in the air. Even at the South Pole. It's 7 times higher than carbon dioxide at the South Pole. Now, what we've got is water vapour is 0.2 to 4%, or if you like, the parts per million, 2,000 to 400,000, 40,000 parts per million at the tropics. Carbon dioxide is only 0.04% at 405 parts per million. So it is important to see that carbon dioxide is low concentration. It's also important to see that methane and the other gases are even much, much lower still. But I'll pick this up as we go through this in a minute. Let's have a look at this, first of all. What are the top 4 gases? I was going to ask you to pick them. The top 4 gases are nitrogen, 77%, oxygen, 20.7%. A typical day here, 20 degrees C and 75% relative humidity. That's 1%. And it's interesting to see that it's 99.8, there's not much left over, 99.8% of the atmosphere has those top 4 gases. So what's going to affect most of the action in the world? Those ones. And it's interesting to see that water vapour is the only condensable gas in the atmosphere. That makes a big difference, and it's called a greenhouse gas. Now, it's a stupid name because a greenhouse has walls and a roof. There's no walls in this roof in the world, and there's no roof. Greenhouse simply means when radiation comes into a proper greenhouse, it heats up the environment because the air can't get away, and so it just keeps heating it up. Like your sunroom, if on a hot day, people come to church, you get cooked on that side if the sun's coming in, because the energy's coming through the glass, it heats you up, you radiate energy, but it can't go through the window. It's a different wavelength, so it can't get out. So it becomes a wall. So glass lets radiation, solar radiation in, but won't let much of it out. It will, but it's not much. Now, if you see that, then you'll see that carbon dioxide is way, way down. It's a trace of a trace. It's number 5, and it's a long way down. And if you be honest, and we can do, this is provable, that man-made contribution is a 20th of that. So you've got 1 part per million going up each year, and a 20th of that is due to man-made. And it's easy, you mentioned the figures, the carbon dioxide is mostly in the sea, 38,000 billion tonnes in the sea, 5,000 billion tonnes on the land, 5,000 on the land, get that right, 38, 2,000 billion tonnes in the land, and only 850 billion tonnes on the earth, and there's only about 40 due to man. So 40 billion tonnes. So it's quite small. So these are facts. You can look them up on the web yourself, and as I said, it's in the paper there with all the facts and where to get them. Now, in a lecture hall like tonight, maybe it's not so crowded, but we'll get to about 1 to 2,000 parts per million, not 405 of carbon dioxide. If you go to a crowded bar, and like to say, or a karaoke bar where you're singing a lot, as someone said, it's better to dine, wine and recline than to snooze, booze and carouse. But if you happen to go to a bar, you'll get up to about 2,500 because there's people all over each other. Submarine guys on atomic submarines live many months at 5,000 parts per million carbon dioxide. So it's not dangerous, it's perfectly livable, and they do have it anyway. And that's on the web, you get on the site yourself, look it up. Now, out of your gob hole, that's this front portion of the anatomy development, if we measured the carbon dioxide there, it's 40,000 parts per million. Now, most of you people are not breathing at the moment, and I'm talking, so I've got a lot of carbon dioxide coming out of my gob hole. Plants die at 150, that's the other extreme. So it's what makes oranges? Carbon dioxide. What makes cellulose, sticks, leaves, flowers, blossoms, the skin of the orange, potatoes? Carbon dioxide. It's the natural thing. And why do they pump carbon dioxide into a greenhouse? To make the crop yields better. And you've heard about the greening of the world in the last several decades. So carbon dioxide is pretty valuable. It's like the fossil fuel. It's a fuel for the plants and growth. So water vapour then is the highest concentration of greenhouse gas. It's 2 to 100 times greater than CO2. And of course it phase changes. Nothing else does. Now let's go on, if you're still with us there. It's high concentration, it's all the one factor in your head. The second one is radiation. Now we know the sun spits out ultraviolet, visible and infrared radiation. Now there's a bit more, the gamma and X-rays and a few particles as well coming too. But of that, only 56% of all the solar radiation ever reaches us on this planet Earth. So it's not a large quantity, but it's about 50-50 infrared and visible. And of course the ultraviolet, of course, is about 8% of it coming in. And fortunately, oxygen is our greatest friend. Up in the stratosphere, the radiation, UV, B and C, hits the oxygen, breaks that up, forms an ozone, uses up the energy. So all we get coming in here is mainly UVA, which causes little, for old fossils like me, you get little, some things we get, even young fossils and non-fossil could get little growths and problems, and you have to get them taken off. It's the UV on the beach that does the thing. IR will keep you warm. So you see, we've got eyes that pick up visible. The skin is full of eyes that pick up infrared. Oh, okay. Well, I'll have to speed up a bit. Sorry. Okay, so what we've got is mainly infrared. So let's have a quick look at this. If we've got UV, invisible light, we've got red, orange, yellow, green, blue, indigo and violet, and we've had the prism at school where we put white light through and we've got red through to blue, and we've seen that on the left-hand side go from indigo violet into ultraviolet, and on the right-hand side we go from red to infrared, so slightly different wavelengths. And it's important to see how much is absorbed. Well, carbon dioxide doesn't do much, it's got a couple of bands, but it only does a little bit there, as you can see, 0 to 100% absorption. Water vapour has 7 bands, and it absorbs a lot more. In fact, there's 3 at 100% and 2 over 60, 70%. And carbon dioxide has to compete with water anyway. So the radiant energy wavelength, as you can see from here, is 0.2 to about 3, whatever that means, micrometers. But it's interesting to see that water vapour is about 5 times more effective than CO2. And it's 50 times more effective than man-made CO2 because it's a 20th of the other. Now, water vapour trumps. And you might say, well, what about methane and nitrous oxide? Well, let's have a look at that. I stripped it, use the same graph, and I'll strip it out. So have a look at that. Nitrous oxide has virtually no impression. Methane has no impression. By the way, it's a low concentrate, very low, much lower than CO2. And so it's not, and we'll just compare it with CO2. So what we've got is all 3 non-condensable greenhouse gases have very little effect on solar radiation. Now you're not told this but this is the truth. Look it up yourself. As I said, you don't need me, I'm just pointing out the web page to go to. So non-condensable greenhouse gases are not major. Now, once the sun's energy comes to the earth, it re-radiates back out again. And so from the earth, what we have is a different wavelength, 3 to 70 micrometers. That won't interest you too much. But what happens with carbon dioxide? Well, there's 2 more bands. They have 4 altogether. It's only got 4. They're a little wider, and they go to 100%. But let's have a look at how much. Let's have a look at water vapour. Now, it's a log scale, so water vapour operates over 85% of the whole range of all re-radiation energy from Earth. So what's going to happen with humidity and clouds and water vapour in the air? It's going to be affected by the water vapour. Now, water vapour on the radiation from Earth is 12 times more effective, or 120 times more effective than man-made CO2. And it's got to compete as well. So carbon dioxide, radiation only. Water vapour is radiation superior. Now, we've already talked about the sun as a key and cosmic rays and so on, but then after you have the sun, the next thing that it does, it works on the seawater, then it works on humidity, and then it works on clouds. Now, if you missed that out, and I just recently, the report from the government, Simon Upton's report, didn't even mention water vapour as a key greenhouse gas. It kills the other greenhouse gases, both radiation in and radiation out. That's my only political point so far. So let's have an example. They say a picture's worth 1,000 words, so I'll give you a Christmas present on this example too. Now, I give this because it does open up insights into what's happening. This is for all of the USA in 100 years, the percentage hot days over 35°C. So the graph is like that, and what happens is that we've gone in the US, because they've got more weather stations in the USA than anywhere else in the world, and of course it's gone from 6% to 4%. It's gone down, but if you take the same weather stations who have also got the carbon dioxide data, the carbon dioxide went up 100 parts per million in the US. This is on the web, you can get it on the web. The hot days went down, but carbon dioxide went up. So the question again is to ask honestly, can you mathematically connect them? The answer is no, and as a scientist, engineer, mathematician, or whatever, modeler myself, I can look at the facts. Let's just quickly summarise the facts. Carbon dioxide, number 5, and small. Low concentration, low, non-condensable, only affects radiation, and it's port that anyway, both in and out. By the way, we can send slides if you want some, if you'll take some notes there. Now, I'll give you a bit of surprise. This is not advertised widely, but it should be. The worldwide average temperature has been the same for 20 years. And I'll give you very strong evidence, which is not, this is my evidence, this is nothing to do with my research. This was put out by the UK Met Office, by the National Post in 2013, and from, you see it's flat right across the top? 800-degree rise from 97 to 2012. But we've got better proof than that, and that's the satellites. The satellites have only been operating just over 40 years. And this is satellite data, and you can see we've got some spikes, but the average temperature hasn't gone up in 40 years. That's actual data. This is not models, this is actual data. So we can see why the spikes. Well, the spikes are due to El Nino, and the spike down is due to the Mount Pinatubo cooling because of dust particles. You remember that big jet from America, the British Airways 747 got caught in one of those where the dust and volcanic ash in the air is enormous. Okay, so it's pretty straightforward. There's 20 years of that. So in the atmosphere, then we have concentration, radiation and phase change. Water vapour is the only condensable gas. It forms a cloud, an umbrella. If you go on a hot sunny day and the cloud comes, you phew, oh, it's an umbrella. Then it rains, it cools the atmosphere, scrubs the atmosphere, and it also scrubs some of the pollutants out of it as well. So water vapour, I'll just give you a quick example here, because at north, down the poles, or in cold New Zealand, it's 8 times as high. 20 degrees is 27 times higher. So out here now it's probably about around that order, 27 to 35 for a time. And at the poles, at the tropics, it's over 100 times higher than carbon dioxide, which is low concentration and doesn't condense. I just want to highlight a couple of things. Yeah, okay, I know he wants me to finish, but I think it's important. Okay, he's going to jump on me. Okay. Well, look, the temperature went up. If the temperature goes up 1 degree, he said, temperature's gone up 1 degree in 100 years. Well, we didn't have many measuring stations, no measurements on the sea. But let's say in 100 years, it was caused by carbon dioxide. So if we get a 1 degree rise in 100 years, it's fair to say that water, the land, everything went up 1 degree. Got to be fair. Everything went up 1 degree in 100 years. Well, if the atmosphere was 14 degrees approximately, and it's gone to 15 now, then in 100 years, water vapour would have gone up 490 parts per million. In other words, not 100. So most of the increase in 100 years must be due to water vapour. It must be. You can't, in logic, there's no logic in blaming it on carbon dioxide. You can't look at carbon dioxide by itself. It's impossible, because it's too small anyway. And so it's pretty straightforward that most of the 1% increase has been caused by water vapour. It must be at least 80% of it anyway, 70%. Now, I don't think I'll have time to do this because you won't want to do it, but I need to just to highlight something here that I was in the car the other week. This is not the same data, but basically I drove out and it was 18 degrees. I got to 23, drove along, looked at the thermometer in the car as I normally do. Started to drizzle, then it rained, went back to 18. Now I didn't die, 1 degree didn't kill us, I didn't get any trouble. But in a few hours it went up 22 times, if you like to look at one condition of relative humidity, and 70 times in a few hours the carbon dioxide did in 100 years. So these data are easily obtained, and I'll give you the program to find it on the web. And I won't have time to go into this, but to say this, for no temperature rise at all, a 3% rise in relative humidity gives us 4 times the amount of carbon dioxide in 100 years. No temperature rise at all. And you've just got to know a bit about humidity tables or humidity calculator to prove that. Now, I'm right at the end, so if you don't mind, this is a key. If you forget everything tonight, let's say this. Water vapour is self-buffering, self-regulating, self-compensating and self-restoring or self-correcting. Water vapour is self-buffering, self-regulating, self-compensating and self-restoring because it moves to the conditions you want. It doesn't need any temperature to do that. Now I'm going to have, if you don't mind, I'm just going to see if there's a finish line, if you let me finish. Okay. Carbon dioxide is not the key issue. By the way, there's not one single paper in the world proving yet that man-made carbon dioxide is the cause. What's the real problems? I think we should highlight that. The real problem is atmospheric pollution, and that is incomplete combustion mainly. I don't know why they allow diesels on the road. The carbon particles are so small now they get in your lungs, they can't get off. Not all of them, but some of them. Bad news. And global dimming. If you look up the thing on global dimming, it's a big thing. You go on the web and have a look at that. And the real problem today is that all the science, NIWA and others are relying on models. You can't model clouds. They put a factor for clouds. They don't put a model. You can't model humidity. And so it's important to see that that's important. Okay. So